Oke, baik, selamat siang semuanya. Suara saya bisa terdengar? Tes, 1, 2, 3. Halo. Tes, 1, 2, 3. Oke, kalau sekarang kedengar nggak? Tes, 1, 2, 3. Masih ya? Oke, baik. Okay, so let's start this session. We already in session 7. So session 7 talk about geometrics and linear transformation, and uh, this is the last session before you doing mid exam. So in this session, I will introduce some transformations, some geometric transformation, but in we apply a transformation using algebraic approach, or the transformation will be directly compute or uh, uh, um, compute or calculate using algebra. So one geometric transformations, many geometric transformation in two-dimensional and three-dimensional using algebraic formula. There are two ways to represent a geometric transformation using algebra. The first one, we can use a matrix. So the linear transformation, it can represent by a matrix. We can multiply the vectors to transform the vectors. And the second one, we can use the inner product. So some transformation use projections and sum of the addition of vectors. Okay, what transformation we will study? There are projections, rejection, flexion, rotation. So first, I will explain the algebra form of this four transformation. Okay, and then I will introduce the general projections projection, reflection, and rotation. This is kind of a linear transformation. So linear transformations, all linear transformations can represent using a matrix. Okay, now what is a projection and rejection? We can define projection and rejection using a vector. So uh, we will project or reject vectors using a line. So if we want to project doing projection and rejection of a vector, we need a line. Okay, so consider a line L of direction U. We know that every line has a direction. What is a direction? Direction means a vector, which parallel with the line. So if the illustration like this, if we have line, then the vector which parallel with line L is we call the direction of the line L. And if U is unit vectors or equivalently U, the norm of U is equal to 1. We call U is unit vectors. So this is a vector which parallel with the line L, and the norm of this vector, the norm of U is equal to 1. So let we A is any vectors in a plane or in a space. Okay. So a vector A, it can be xy or it can be xy z. This is A, and this is the line L. So by addition rule, we can find two vectors. We can find two vectors such that A is the sum of these two vectors. Okay, the first vectors is parallel to the line L, and we denote it by this one, A, and a parallel symbol with the subscript is the parallel symbol, the parallel line. Okay, and the second vector is orthogonal to these vectors, and we denote by A, and this is the symbol of orthogonal. So by addition rule of vectors, remember we have addition of two vectors, a rule addition of two vectors like this. If is the vector B, okay, and this is the vector C, then this is the vector B plus C. Okay, so we can see that A is equal the this is the projections, and this is orthogonal with the projection. So A is equal this one plus this one. So every vectors can be expressed as the sum of these two vectors. One parallel to the line, and the other one orthogonal with the line. So we call A with the subscript parallel line is the projection of A onto line L. So this is the projection onto line L. And the other one, this one is the rejection. So remember, this is a projection like the shape or the shadow of A in a line L. And the rejection is orthogonal to the line L. So this is the projection and this is the rejection. So this is the first two of our transformations, projection and rejection. And the third transformation is reflections. And we know that if we want to reflect, we need an axis or a line as a mirror. So let us call the vector A with subscript. This is the symbol like T, but it means the reflection of the orthogonal symbols. We can see this the reflection of orthogonal symbol. The orthogonal symbol is like this, but the reflecting is we reflect the orthogonal symbol. So these vectors is the reflection of the vector A. So the reflection of A to the opposite side of line L. So this is the reflection of A using with respect to the line L. You can see you can imagine this like a mirror. We reflect, and the shape or the shadow of the vector A is this one. Sorry. Okay, now how we compute the projection, the rejection, and the reflection if we given any vector of A, any vector in 2 dimension or 3 dimensional. How we compute, for example, how we compute if we have a vector 2, 3, and we have a line L is with the equation y equals 2x. Okay, and we project these vectors A to this line, and we reject the vector A using this line, and we reflect the vector A using this line. How we find the mapping, the mapping of A using projection, using rejection, and what is the result of this transformation, these 3 transformation. If we projection A to L, what is the vectors? Okay, and using the geometric of the dot product or inner product, using the geometric of a vector in 2-dimensional and 3-dimensional, the inner product, we get this result. So how we compute using the inner product, so the projection of A onto line L of direction U of direction U, and U is a unit vector. Okay. So the projection is the inner product between A and U times the vector U. So we multiply the inner product of this A and U multiply with the unit vector U. Addition, the role of addition in vectors. And the rejection, the formula of the rejection of A is equal to this formula, minus A plus 2 times the inner product between A and U times U. Have but with but not unit vectors. So if you have a direction of line L, but direction is you can normalize, you can divide by its norm, so you will get a unit vector. So if the direction if U is not a unit vector, if U is not a unit vector, then you must copy the statement of proposition 2.11. So okay. So the example is the vector, we use the vector in two-dimensional, and the inner product we use the Euclidean inner product or the dot product, the usual dot product. Okay. Let say let A be the vector okay. So we try A is 2, 3. So vector 2, 3, you can imagine 2, 3, and the x coordinate the Cartesian, and L, the line L is the line with the line equation is y equals x. So this is A and this is the line y equals x. So if we see the picture or if we want to look the picture, this is xy coordinate, and 2, 3 is 1, 2, 1, 2, 3, and this is A. Okay. This A. And where is the line L? The line L is 1 equal to x. So if x1, then y plus 2. So the line is passed through the origin. This is the line L. Sorry. The line must pass through the origin and pass to passes to the point 1, 2. This is 1, 2, 1, 2. So this is the line L. Now we want to project the vector A to the line L. We want to find the shadow in the line L, and we want to find the rejection of A and the reflection using the formula in the proposition 2.11. Okay, but in this proposition we need what we need in to complete this transformation. We must find first we must find the direction of the line. You know, how we can find the direction? If we want to find the direction, we can find by you take 2 points in the line, two sample points in the line. So we can see that okay. So first we find the direction, the direction of the line. Of the line. Pick 2 points. Pick two. Choose 2 points in the line L. Choose 2 points in the line L. For example, we can choose A is the origin and B is 1, 2, 1 and 2. So this is 2 points in the line on the line L. A 0, 0, the origin, and the second is 1, 2, 1, 2. So this 2 point on the line L, and the direction we can choose, or we can compute the direction of the line L is the vector. We can just the direction of the line L is the vector AB. So what is AB? Do you know what is the vector AB? Anyone? Anyone can tell me what is the vector AB? Oh, so this is my vector. Not bar, but row.
Satu dua ya Pak.
Apa?
1, 2.
1, 2, okay, good. 1, 2. Yes, correct. That's right. So I need arrow. Okay. So you can calculate by subtract b minus a. Subtract b with a. So this is 1, 2, 2. This 1, 2, 1, 2, 3. So this is one of direction or a vector which parallel to the line L. Okay, 1, 2. We can choose a scalar multiple OABs. For example, we can choose other direction like 2, 4, 3, 6, or we can also choose 1, -1, or and -2. Because a direction means a vector which parallel to the line, and so many vectors parallel to the line. But we choose only one for computation. Okay, and next, so we already have a direction, but I would like to ask, is this the direction unit vectors? Is this a unit vector? So the question is AB, this AB, the vector AB, is unit vectors? Is the vector AB unit vectors? Because if we want to use this formula, then you must unit vectors. The direction is unit vector. So you must check, is this direction is unit vectors? Do you know unit vectors? What is unit vectors? Anyone? Is AB unit vector, or equivalent? Is AB the norm of AB? The length of AB is 1. Is the length of AB 1, or the norm of AB 1? Anyone? Jadi vektor AB ini unit vektor bukan? Panjangnya 1 bukan?
Bukan, Pak.
Bukan ya? Yeah. So AB is not a unit vector. This is not unit. Then, because this is not unit vector, because what is the length of AB? Do you know the length of AB? The length of AB is berapa lengthnya? Berapa panjangnya? Length of AB is
Akar 5 ya, Pak.
akar 5 ya, square root of 5. The norm of AB, the norm of AB, okay, the norm of AB is this is the square root the square root of 1 square plus 2 squares. Oh, sorry. Plus 1, 2 squares. Square root of 5. So AB is not a unit vectors. So we must normalize. We must divide AB with its norm. So the unit vector U so AB divided by its length. So divide by or multiply by 1 square root of 5. 1. So this is 1. So 1 square root 5 just to square root 5. So this is U, the unit vectors. The direction U is the unit vectors. Okay. Then the projection of A, the shape of A in the line L, the projection of A on the line L, projection, okay, yes, the projection. This is projection, and we use the subscript, the parallel symbol, parallel symbol. Okay, this one. Okay, so the projections equal to the inner product because we using the Euclidean. The inner product is the dot product. The dot product. The dot product A dot U, A dot U. Okay, I guess this one. A U multiply by U. Okay, so this is the projection, the shape of A in the line L. Okay. So where is the projection? The projection, this one. Okay. So this is the projection of A. Okay, and the vectors is we compute this is A. Okay. dot product with u. This is u. Dot product u, and we multiply by the vector u, the unit vectors. To complete the dot product, the dot product is 2 times 1 square root 5. So this is 2 square root 5. Okay, plus 6. Yeah, 6 square root of 5. Okay, and we multiply by so, yeah. Okay, complete this one. This one is 2 plus 6, 8. Okay, and multiply by. Okay, so the projection is sorry, projection is okay. So this is one fifth, and 1 fifth, and 16. Okay, so this is the projection of A on the line. Also 1 fifth and 16. Okay, any questions for the projection? Ada pertanyaan nggak tentang projection? Okay. After that, we can continue to find the rejection. We already have this. You can see this is the projection. So the rejections is the subtractions of A and the projection. So if we continue, what is the rejection? The rejection is yeah, this is the rejection. This is the rejections. So the rejection is A. This is A minus the projections minus the projection. You can see this is the projection of A. So we have now the projection is this one. Okay, and what the result is, what is the result? The result is 2/5, 2 times 5 times 10 minus 8, so 2 3 times 5, 15, 15 minus 16, minus 1. So second is minus 1. Okay, this is the rejection. And if you remember, what is the relation between the projection and the rejection with our vector A? So the vector A, you can see, you can you can get the the relation using the picture of, or the by the rule addition of factors. A is the projection, is the projections plus the rejection. Plus the rejection. Okay, so 2, 3 equals to the projection. This is the projection plus the rejection. Okay. So this is the relations between A, the projection, and the rejection. Okay, any questions for the formula or the example of projection, rejection, and okay? So we can write the A is the sum of projection and the rejection plus the sum of the projection and the rejection. Okay. And for the reflection, you can compute using this formula. So if we want to reflect, or we want to project or reject the one factor to the line L, we have algebraic formula in proposition 2.11. And the question is how, from where this formula come from, why this formula is correct. Okay, so I will prove just one formula. Okay, so I will prove the formula of the reflection. Okay, so let's see these pictures. Okay, so this is A, the vector of A. Okay. And this is the line L. Okay. But the line L is here. You can see that the factor, we can move the factors like this. So we can imagine this is the line L, because we can move the vector A to move ke, jadi kita bisa gerakkan vektor A ke garis ya, sampai ujungnya di garis. Oke. So the 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 reflection is the sum of A, okay, plus the minus of rejection, okay, plus the minus of the rejection. So we can A, the reflection by using the rule addition of factors. So the reflection A, the reflection of A with respect to the line L, the reflection is A, okay, plus minus of the rejection, because the rejection is go up, and we need the opposite of rejection. So this is plus minus or minus of the rejection of A, okay, and plus again we need the opposite of the opposite factor of the rejection. So this is plus minus of rejection. Okay, you can see A, the opposite of the rejection, and the opposite of the rejection. If we sum these three factors, we get the reflection. Okay. Then if we write all the formula of these three factors, or the formula of the rejection, okay, sorry. So from the illustration, we can see that the reflection is, okay, sorry. The reflection is A plus the opposite of the rejection, the opposite of the rejection. So plus, we'll give the okay. So this is the reflection. The reflection of A is A plus the opposite of the rejection. The opposite of rejection is minus this one, plus minus this one, or plus 2 times of the opposite of the rejection. Okay, and then we substitute what is the formula of the rejection from proposition 2.11. We know this is the formula of the rejection. So we substitute rejection is A plus 2 times the formula of the rejection. Okay, A minus the inner product, the inner of A minus the inner product A and U. Okay, times U. Okay. So this is the rejection from the proposition. Okay. Oh, sorry, this is minus of the rejection. So this is minus and this one was plus. Uh, we simplify the equation a plus minus, so minus 2a, okay, plus 2 times this one. Okay. A minus 2a is minus a. So this is equal to so here minus a plus 2 times this one. Okay, so we get the formula. We get the formula minus a plus 2 times inner product of any a and u times u. Okay, so that's the proof of the formula, and how we know this the projection is the inner product of u. This one you can see in a linear algebra course, the proof, and the a minus the rejection a minus just from the rule, the addition rule, the rule of addition of two factors. So we continue to the next transformation. So in the proposition 2.11, we talk about the projection, rejection, reflection for a line. How about the projection and rejection with plane? So the picture is like this. If we have the vector A and we project, we find the shape of the vector A in the plane. So this is the vector A, and the projection is the shape or the shadow of the vector A in the plane. So this is the projection, and the rejection is orthogonal with the plane, orthogonal to the plane, or orthogonal to the projection. So we also have the same result. A vector A is expressed as the sum of the projection and the rejection to the plane. Okay, this is the projection on the plane. This is the symbol of the rejection. Okay. And we can also reflect the vector A using this plane. So the mirror is the plane. The previous is the mirror is the line. Now the mirror is the plane. And the result of the reflection or the mirror image of A, we also use same symbols. A orthogonal, but we flip. So we flip horizontal. Yeah, we flip horizontal, or just like the letter T. Okay, this is the reflection. And how we compute the projection, the rejection, and the reflection using the inner product, using algebraic algebra of vectors. And we get the formula in the proposition 2.12. Yeah. This is the projection A onto plane E. This is the rejection projection, rejection and reflection. Okay. So a different approach, uh, how we compute, how we find the projection, rejection, uh, rejection and reflection. A different approach, we can use a matrix. So all these three transformations in linear algebra, it, it can be represented by a mapping. So projection just like a mapping from a vector to a vector. Reflection also from projection is from A to this symbol. Uh, the rejection is this one, and the reflection is this one. So these three transformation is a mapping from one vector to a vector, and this mapping, these all three transformation, these all three mappings has a properties of a linear mapping. So, why we call this linear mapping? Because it preserves sum and scalar multiplication. What does that mean? It means if we sum two factors and then we map this the sum, then this is equal if we sum, if we mapping two factor and then we sum. So if we have a two factors a plus b and we mapping, we project a plus b, we projection to the line or to the plane. Okay. Then this is will equal to the mapping, the projection of A plus the projection of B. So this is the meaning of a preserved sums. Okay. So the meaning is this one we sum first and then we map the result, the vectors. Then it will be same with if we map each vectors, if we project each vector and then we sum the mapping. Same with scalar multiplication. If we multiply the vectors with scalars and then we map or we project these vectors. This one will be equal to we project vector B, and then we multiply by scalar. So this means preserve scalar multiplication. So if this equation is true for all scalar alpha and all vectors, then we call this the mapping or the projections preserve sum and scalar multiplication. Or we simply say that the projection is a linear mapping, but the rejections also a linear mapping. And in linear algebra, we know that a linear mapping, a linear mapping can express by multiplications. We can express a linear mapping as multiplication by matrices. So in the formula of projection in proposition 2.11 and 2.12, we use the inner product. The formula is using the inner product and the properties of addition and the properties of addition. But we can also see the projection and rejection as a multiplication by matrices. So if we want to know what is the matrix, what is the matrix of projections, then if we regard factors, so if we regard factors as a column of numbers, remember A, we write A as a column factors 2, 3, okay, and U also a column factors, okay, a column factors. Okay, 1 square root 5 and 2 square root 5. Yeah, this is unit factors. Okay, and from the formula in the propositions, then the projection is the dot product. Okay, the dot product A and U multiplied by U. Okay. Okay, but we can write the dot product A and U. We can write the dot product A and U by a multiplication of two matrices, a multiplication of U transpose and A. Okay. The U transpose U transpose multiply with A. U transpose multiply with A. So this will U transpose multiply with A and multiply again with U. And we can check this one equals to U multiplies by U transpose multiplies by A, or this is U multiplied by U transpose and multiply by 8. So if we what is the U multiplied by U transpose? If we have the U is this one, so U times U transpose. U is column factors, 1 square root of 5, 2 square root of 5. Okay. Then U transpose is a row factor, so U transpose is 1 square root 5, 2 square root 5. And what is the size of this multiplication? The size is 2 by 2, 2 times 2. 2 times 2, and this is 1 fifth, sorry, 1 fifth. Okay. In the row, and then this, sorry, this is 2, 1 times 2, okay, 2, 5, okay, and then 2, 5, and then 4, 5. Okay, so the projection is the multiplication this 2 by 2 matrix with A. Okay. So this is the matrix. The matrix is the multiplication between U as matrix times U transpose. So we write U as a matrix. Sorry, a column matrix. So U times U transpose is 2 times 2 matrix. Okay, so these 3 transformations, the projection, the rejection, and the reflection, is a matrix times the vectors. Yeah, a matrix times a vectors. We multiply a matrix with the vectors. Okay, the rejection also the matrix. This is the matrix. Multiply with A. Multiply with the vectors, and the reflections also the multiplication between a matrix with the vector. So all this transformation is linear transformation because we can find the transformation using multiplication by a matrix. Okay, this is for this is the formula of the matrix of the projections. Okay. Just compute the matrix U times U transpose, and we get this matrix. So A, in this case, A in R3 in the space, A in X, Y, Z. Okay, and the matrix is like this. Okay, this is projection matrix, and this is the rejection matrix. Okay, so all have the matrix. The reflection, this is the reflection matrix. From the unit, the direction of the line, the direction unit vector of the line. Oke, jadi 3 itu bisa dihitung pakai matriks, dan caranya adalah kita harus buat dulu matriks transformation-nya ya. This called the transformation matrix. Oke, dan untuk mendapatinnya tinggal dikaliin aja dengan si vektor A. Okay, this is projection matrix for plan. Okay. Oh, sorry. The symbol n. This means the normal vectors. The vector the orthogonal to the plane. Okay. So n is like this. If this the plane, then the normal, the vector n is the vector which orthogonal to the plane. So this is orthogonal. This is n. Yeah, you can see in the previous slide. Yes, the vector n. This is the n. Okay. So the projection on the plane also a linear mapping, also linear transformation. So it has a matrix transformation. This is the matrix, the projection matrix for plane. This is the rejection matrix and the reflection matrix. Okay, so we already know the algebraic approach, the algebraic formula for three transformations, yeah, projection, rejection, and reflection. Next, we want to discuss about one kind of geometric transformations. This is another popular transformations. So next we will talk about rotation. But any question for projection, rejection, and reflection? Ada pertanyaan nggak tentang tiga yang tadi? Oke, berikutnya kita akan coba bahas rotation. But again, we will study rotation, this transformation by two approach, using the inner product, using the sum or the subtraction of vectors, and the second we use the matrix. Jadi kita akan melihat bahwa rotation itu bisa kita punya dua cara ya. Satu pakai inner product, satu pakai a matrix. And the result always same. The result will be same. Okay, so for rotation, okay. First, we given a vector A. This is the vector A. Okay, and to rotate these vectors, we need a line. We need an axis, a line. Okay, and a line. This is the line L. Sorry, the line with the direction L. This is the direction vector. Okay, and we also assume this direction is a unit vector. So the direction also a unit vector. Okay, so we have vectors and we have a line, an axis. Okay, and because we want to rotate the vectors, then we need an angle. Okay, and the angle is, so we want to rotate a vector A. So a vector A is rotate, this vector rotate to the vector A action, okay, around an axis. So this is what we call this, around an axis L. Okay. So we rotate, and the angle is construct in the line L. Okay, suppose a vector A is rotated to AX action around axis L along a unit vector L by angle omega. Okay, so we rotate A, the angle is omega, and the axis is aligned with the direction L. And suppose that the starting point of A is at the origin. So this is if this in this, so this is 0, 0, 0. Okay, and let P and P action be the endpoint. So this is the point of P, and this is the point P action. Okay, so the assumption the assumption is we have three things, the factors, okay, a line, and angle, okay, omega. Factors, the line, and the angle. Jadi kita pasti akan selalu butuh tiga ini. The factors yang mau di rotate, okay. Line, jadi line itu kayak apa, pusatnya, the center, okay. And the angle, ya, berapa degree kita mau rotate. Jadi tiga itu. Nah, the result of the rotation is A action. So A rotate, and the result is A action. Or if we look the endpoints, P to P action. Okay. The first is a vector notation, and this is the point notation. This is vector rotation, and the second is the point rotation. Okay. So how we find the result, the rotation? Okay. A vector rotation. Now we compute by using vectors and inner product. So if we look A action, this one is action with endpoint P action. A action, the rotating vector is the sum of three vectors. O key, okay, rotating vector key, this one, key H and HP action. Okay, so if we can compute these three vectors, we get the result of the rotations. Okay. If we know O key, H, and HP action, we will get the vector rotation. Okay. And what is O key? The vector O key. The vector O key, you can see the vector O key is the projection. Okay. The projection of A, okay, to the line L. Yeah. So by the proposition 2.11, we can compute the vector OK. Okay, the inner product A and L multiplied by L, multiply with L. Okay, so this is projection of A. Projection of A on the line L, okay, on the line with the direction L. Okay. Okay. And what is QP? Sorry, this is QP. QP, what is QP? QP. Okay, QP is the rejection. Okay, this is the rejection. The first is projection and this is the rejection. We already know the formula of rejection. So this is projection and this is rejection. And what is key H? Key H is on same direction with QP, or this is the multiple of KH is the multiple of QP. Okay. So if this QP and KH is have a same direction with QP. So QH is a multiple of QP. And what is the multiple? We can prove that the scalar is cos omega. Cos omega. And HP action is you can imagine HP action is a cross product, a vector that orthogonal to a vector L and orthogonal with the direction L and orthogonal with QP. And we can prove that HP action is L cross A, so we cross two vectors L and A, and then we multiply with sin omega. So we can compute OK, we can compute QH, we can compute HP action, all using inner product, in projection, rejection, and cross product. So this is the vector rotation. And the formula of the vector rotation is A cos omega plus cross product L and A sin omega plus this is just substitution of the previous formula, this formula. Okay, Jadi kalau mau rotation, ya ini formulanya, ini rumus. Tinggal masukin omeganya berapa, direction line-nya berapa, A-nya berapa. Nanti cara hitungnya pakai cross, inner product, dot product, and cos and sin, jadi trigonometry, cosinus and sine. Oke. Okay, and rotation also a linear mapping. It means a rotation is a multiplication with a matrix. A vector, we multiply a vector with a matrix. So, and the question is, what is the matrix? So, if we see this as a multiplication by matrices, what is the matrix? Because rotation is also a linear mapping, just like reflection, projection, projection. All this is linear transformations, all linear mapping. And all linear mappings always have a matrix transformation. So, and the matrix is, this is the formula of the matrix of rotations. In three-dimensional space or in space. Jadi ini matriks rotasi ya untuk formula yang sebelumnya. Jadi karena kita butuh axis, butuh angle, okay, pasti ada L, there is an angle. So the entry of the matrix rotation is from the angle and from the line, from the direction. Yeah, cos, L1, L2, L3, sin. So the result from matrix and the result from proposition, the formula in this proposition will be same. Jadi hasil di sini sama hasil pakai matriks itu pasti sama ya. Asalkan lainnya sama, A-nya sama. Okay. Okay, this is just a special transformation. We call orthogonal transformation. So an orthogonal transformation is a transformation such that the norm and the inner product are preserved. Jadi after transformations, the vectors, the norm of the vectors, and after transformation will be equal, and also the inner product. Okay. And orthogonal matrix also linear transformations. And what is the example of the orthogonal transformation? So rotation and reflection are orthogonal transformations. Okay, this is just how we sorry, Okay, how we find a matrix for any linear transformation. Okay. So the matrix from linear transformation is from the coordinate matrix for order basis in V and order basis in W. Okay, if we have T is a transformation from V to W. So we can find the matrix transformation if we have the order basis from P and W. Okay, I think that's all for this session. Any questions? Okay. If there's no question, I will end this session. So this is our last meeting before mid-exam. Okay, thank you for your attendance and your participation. See you next session. See you next time.
Makasih, Pak.
Terima kasih.